Okay, welcome to lesson 9. And so we're starting the mechanisms, and the first mechanism, and I think arguably the most important mechanism in organic chemistry, is what's called the SN2 reaction, or uh, substitution nuclear bimolecular. So we're going to be breaking this down. All right, what does this mechanism involve? It involves the collision between a nucleophile and an electrophile, where we have a group that we're going to call the leaving group, which is abbreviated LG. The leaving group is the group that will actually be leaving the molecule, and the nucleophile is as we've already defined, is a molecule or even an atom which has a pair of electrons that's available to form a bond. This is a Lewis base. It may or may not have a negative charge on it. So this is called a nucleophile. The reason why the two molecules undergo a collision is pretty clear cut. And this is a theme in chemistry in general, which happens over and over and over again. And that's the association between something that has essentially either a partial negative charge on it or a formal charge of -1, and the interaction with a particle that has a partial charge of a partial positive charge, or a formal charge of plus some magnitude on it. We've already talked about the concept of the electrophile, the nucleophile, and now we need to put this whole thing together. So the hallmark of an SN2 reaction is that you're going to have the collision between the nucleophile and the electrophile. And it's called a substitution reaction because the nucleophile will be forming a bond with the electrophile. So we have this collision here, the interaction between two particles that have opposite charges on them, a natural attraction between opposite charges, and then the leaving group. So we have a bond forming here. We have bond formation. And we have the leaving group, which is leaving. So we have bonds breaking. So to start with, let's categorize each of the components that are in this reaction. So we have the nucleophile, we have the electrophile, and now we haven't talked about this in detail, we have the leaving group. So the nucleophile, as we've already stated, is a base. It can be weak or strong. Whether it is weak or strong is going to characterize the nucleophile as either being good or bad, in a sense, and we'll talk about that. The electrophile okay, so coming back to the nucleophile, this is also a Lewis base. So it has an electron pair to form a bond. The electrophile, this is going to be a Lewis acid. Lewis acid, so it accepts electron pair to form a bond. All right, and then the leaving group, which I'm just going to continue to abbreviate as LG, this is also a base. Good leaving groups are weak bases. Weak bases. They're highly stable. In terms of their nuclear charge, they have a low affinity. The good ones have low affinity for hydrogen. Good leaving groups are weak bases. When we talk about nucleophiles, the nucleophiles the best nucleophiles are also weak bases. All right, and these guys have high selectivity. High selectivity for the electrophilic carbon, and a low affinity for hydrogen. So there's similarities between the nucleophile and the leaving group. In the case where you have a really strong base attached to an electrophilic carbon, it's going to be a crappy leaving group, and in fact the reaction is most likely going to be inhibited. Now, another aspect of this, which is super important, if you look at the molecule, the electrophile that I've drawn here for this example, you can see that I've set it up a certain way in order to be highly illustrative here. So we have a carbon which is arguably a stereocenter because there are literally 4 different groups attached to the carbon. And I did this on purpose because one of the key features of an SN2 reaction is the fact that they undergo inversion of stereochemistry. So I'm going to write that down here. They invert stereochemistry. So let's go to the actual mechanism now. And in that, I'm going to address this term biomolecular. So if we look at this in more detail, all right, so we have our nucleophile and we have our electrophile here. Let me redraw it quickly. I want to change my coloration. So here's my hydrogen, and then we're going to have R1, and then we have R2, and then we have the leaving group, LG. All right, the leaving group. And actually, I want to change this R2 a little bit. I'll make it more straight down here. So we're going to have R2. All right, so let's talk about what has to happen here. The nucleophile, firstly, in an SN2 reaction, and again, we see this, and I'm going to use my curved arrow, we see this ubiquitously through organic chemistry. I don't care what mechanism we're going to be talking about. At one point in that mechanism, you will have a molecule or an atom that has an unshared pair of electrons on it and may or may not have a negative charge, making a collisional attack on something which has a positive charge on it at some point in the mechanism. SN2s are more basic from that point of view because literally the only 2 molecules that are involved in the reaction are going to be the nucleophile with the unshared pair and the electrophile that has electron deficiency in it. So here is my electrophilic carbon. All right, now in the process of this reaction, all right, so one of the necessities is backside attack. The nucleophile, and this has been proven mechanistically in the science. I'm not going to get into it here, but the nucleophile cannot come in physically from the same side as where the leaving group is. Why? Because number one, the leaving group is bonded to that carbon on that side, and secondly, the leaving group has to leave. So if you bring in a nucleophile from the same side as the leaving group, the reaction is going to be non-productive. It's not going to happen. The other thing to think about is the leaving group is going to have a net negative charge on it, a net negative partial charge on it, and so does the nucleophile. And you guys know from basic physics that this interaction here doesn't work. They repulse one another. So basically, the nucleophile has to come in from the opposite side of the molecule where there's a clear facilitation of the attraction between the 2 charges, and there's not anything in the way for the nucleophile to hit this carbon. And that raises another issue, right? Here we're dealing with the electrophile, and we already talked about the issue of structure, all right? So R1 and R2 can be a lot of different things, and additionally, we could substitute out this hydrogen for literally another R group. So the more structure you have on these three groups here, the more difficult it's going to be for the nucleophile to reach this carbon center. So that's another thing to think about. If both R1 and R2 were simply hydrogens, this reaction would be highly efficient because the nucleophile would have 100% access to the backside of this carbon. As we add R groups to this, the nucleophile is going to have a more and more difficult time reaching this carbon. If the R groups are highly complex within themselves and we were to substitute this H out for another R group, then backside attack might be completely impossible. So we see SN2 reactions happen most often on electrophilic carbons that have very little structure involved in the electrophile. So let's look at the mechanism. I'm going to redraw this. So as the nucleophile comes in, it's going to be forming a bond, which I'm going to draw this way with 3 dots to indicate that. And then the electrophilic carbon is, and I remember we have an inversion of stereochemistry, so I'm going to draw it this way. I'm going to put my H straight up, and the 2 R groups are going to be basically filling out the tips of a triangle. Okay, so this is what we're drawing right now is the transition state. So this is going to be partially positive. This is partially negative. The leaving group will indicate the bond is dissolving, and it will have a partial negative charge. I'm going to put a bracket on this. This is what we call our transition state. I'll indicate this way, where TS is equal to the transition state and what's important to realize is that in the transition state, the electrophilic carbon is sp2 hybridized. It is triangular, planar. Whoops. It is triangular planar. Triangular planar. All right. So what's happening is we're seeing this inversion of configuration. So if this thing started out, let's say, as an R, it's going to end up as an S. All right. And so when we finish the reaction, the stereochemistry will have been inverted. So the H is going to be here like that. R2 is going to be like this, and our R1 will be like this. So we've had a complete inversion of stereochemistry. This is hugely important for the SN2 mechanism because, again, if you're doing organic chemistry in a research lab at the university level, or you're in a biotechnology company where you're producing molecules, if you're utilizing an SN2 reaction anywhere in the mechanism and configuration is important, then you have to recognize that in that process you're going to be changing the configuration, and that can matter. Now, so this lays out the actual mechanism. Now let's take a look at the aspect of the bimolecular. So to deal with that, we're going to draw an energy diagram here. And we don't know anything about the thermodynamics of this generalized reaction, right? So I'm not going to pay much attention to, the energy, the potential energy of the reactants versus the products. What we're worried about right now is the mechanism, and that has to do with this hump. So I'm just going to arbitrarily make this into an exothermic reaction. But again, that doesn't matter. What matters are the kinetics, and they are defined by this hump, this thing here. This is where the kinetics are, not thermodynamics. And we have where we're starting with the reaction, the reactants, and this point right here is what we call energy of activation. This is the energy required to activate the reaction. And where is that putting us? So where that is putting us is at the transition state. So that would be this complex here where we have the nucleophile forming a bond. The hydrogen is going to be pointed straight up. My R1 and my R2 are going to be here in a trigonal planar complex. And then we have the LG here. This transition state is sitting right at the top of the hump. It's right here at the top of the hump. All right. And the formation of this is bimolecular. Whoops. It's bimolecular. Meaning that it requires the collision between two molecules. All right, let's call this A. B, the kinetics are a single step. Okay, let me clarify that. C, the rate limiting step, is the single collision. There's only one step in this reaction. So it's one step kinetics. One step kinetics, that's it. All right, and with that, I'm going to close the lesson.